Okay, welcome back everybody. In this video, we'll be finishing up section 8.3. So we, in the last video where we ended was we had worked through this problem involving the environmentalists and their claim involving the waste recycled by adults. We had done it using the critical value method and then also the p-value method and compared the two. So where we'll go next is, I'd mentioned at the start of the last video that typically you don't know what the sigma is, the population standard deviation. Realistically, you're not going to know what that is, but on the off chance that you do, really the only change that you would make is that you then are using the z table rather than the t table, and you're going to use sigma because you know it. Instead of using s, you'll use sigma because you have it. And so that's really the only difference. And so we should do an example involving that. So let's try that here. So here it says the weights in pounds of discarded plastic from a sample of households listed in the back of the book. And the summary statistics are given. The N is 62, the X bar is 1.911, and the S is 1.065. So this was actually a two-part question. This was problem 12, but 32 asks us to redo the problem using the fact that sigma is somehow known to be 1.065 pounds. So we'll start with hypotheses, as always. So the null hypothesis here is, what is the claim? The claim is that the mean weight is greater than 1.8 pounds. So mu is greater than 1.8. So then the alternative is not greater than 1.8. So then we're going to use z this time, because we're told that sigma is known to be 1.065. Our test is right-tailed. We're using a 0.05 significance level. Okay, so then with an alpha of 0.05, that's going to be 1.96. Okay, and then test statistic, z is going to be x bar minus mu x bar over sigma this time, since we know it, over root n. Okay, so then let me calculate that for you. All right, so I've gone ahead and calculated the test statistic. It works out to be 0.82. We had taken the sample mean minus the hypothesized mean divided by the sigma that we were given this time, divided by the square root of n. As it turned out, I had the wrong critical value here. I had looked at the wrong place in the table. It's actually 1.645. Fortunately, it doesn't change our conclusion because the 0.82 is not bigger than either of those two numbers. And so we will fail to reject our null hypothesis, and so there's not sufficient evidence to support the claim. And that will do it. All right, so our next example, in this one, it says an elementary school has 1,100 students. The principal of the school thinks the average IQ of the students is at least 110. To prove her point, she administers an IQ test to 20 randomly selected students, and then we get sample statistics out of that. We want to decide if the principal should accept or reject her original hypothesis. We're going to use a level of significance of 0.01. So we have a null and alternative hypothesis. That's where you want to start usually, is just making up the hypotheses. Okay, she thinks that the IQ's at least 110. So that will be the mean, bigger than 110. Mean is not. Will be our null hypothesis. Okay, and then for this, it is again a right-tailed test. And then on this, do we know the population standard deviation, the sigma? Okay, so here towards the bottom, it says the average IQ of the sample is 108 with a standard deviation of 10. It should be clear that that 10 is the sample standard deviation. So we are going to be using T. We have an S of 10, we have no sigma. So we'll be using the T distribution. The N is 1,100 students. And so that's the population of the school. I need to be careful. She administers an IQ test to 20 people. Okay, so our degrees of freedom is actually going to be 19. All right, so then we'll have to go to our T table and figure out our critical value for that. So let's do that. All right, so the critical value works out to be 2.539. So then we're going to need our test statistic. So that will be x bar minus mu x bar over S over root n. So the sample had an IQ of 108 average. The hypothesized was 110. So at this point, we can really stop, right? Because the sample she got wasn't even higher than the mean at all, right? So there's no way that this is going to support her hypothesis, but we'll follow through with the details anyways. So the sample standard deviation was 10, and her sample size was 20. So we're going to get a negative test statistic, and so that's definitely going to be less than 2.539. But we should go ahead and do it anyways. Negative 0.89. All right, so negative 0.89 is definitely less than 2.539. And so we're going to fail to reject RH0. So there's not enough evidence to support the claim. And if we'd read through the problem, it should be clear of that to begin with. If she thought that the average was going to be at least 110 and our data came out 108, which is not over that, then it's not like we happened to get a sample that supported her thesis just due to chance, right? It doesn't support it at all, right? All right. So let's take a look at another example. All right, in this example, it says an inventor has developed a new lawnmower engine. He claims that the engine will run continuously for 300 minutes on a single gallon of gasoline. From his stock of 2,000 engines, the inventor selects a random sample of 50 for testing. Okay, the engines run for an average of 295 minutes with a standard deviation of 20 minutes. We're to test the claim that the mean runtime is 300 minutes. So it says it is 300 minutes. Probably realistically, we want to see that it's more than that, but the way that it's stated, we'll do it as equal. So the mu is equal to 300, and that's the claim. We want to see, okay, is that possibly not equal to? Okay, our alpha is 0.05. Okay, so critical value first. So we're doing a two-tailed test. Our alpha is 0.05. Our degrees of freedom is 49. And so we need to know what our critical value is. So let's go get that. All right, so for this one, our degrees of freedom was 49, which is obviously one less than 50. And if you look at our table, it starts jumping up by 5, then by 10s once we get out to this point. So what you can do is just use, in this case, 49 is pretty close to 50. If it had been 47, maybe we'd want to average the values from 45 and 50, but as it is, it's just under 50. we'll go ahead and use 50. Our alpha was 0.05 and it's two-tailed, right? So that means the area in two tails is 0.05, so each tail is 0.025. So right in the middle column, we'll use a critical value of 2.009. Okay, so there's two critical values, plus and minus 2.009. And next up, we need the test statistic. So that will be our sample mean, which was 295 minutes. The hypothesized mean was 300 over S over root N. And there were 50 engines that were tested. Okay, so let's go ahead and calculate that. Negative 1.77 for that. All right, so then negative 1.77, that is below the mean, but it is not so low as to be below the negative 2.009. So based on this, we'll fail to reject our null hypothesis. So what that means is the claim was that it was 300 minutes and our sample did run 295 minutes, but at an alpha level of 0.05, we can go ahead and attribute that to chance, basically. So there's not enough evidence to refute the claim. This time the claim was in the null hypothesis, so we can just say there's not enough evidence to refute the claim. Okay, so just for fun, let's go ahead and see about the p-value method for this. So again, we'd be stuck using the 50 row if we have to. And where would our test statistic lie? Again, there's no negatives here, and that's okay. We'll just use the positive version because that's what our t-table has, or almost has. 1.77 in this row, 1.77 would be some column in here. The two-tail area would have to be between 0.05 and 0.10, right? So our probability is bigger than 0.05, right? And that was bigger than our alpha, right? This was our alpha of 0.05. And so based on this, we would fail to reject using the p-value method. Okay. All right, we have just a couple more examples to do. So here, a researcher wants to test the claim that convicted burglars spend an average of 18.7 months in jail. He takes a sample from court cases and finds the mean and standard deviation. We're to test the claim that the mean is 18.7 months. At the 0.05 significance level. All right, so the alternative is going to be not equal to. Okay, so little picture, then critical values. So the significance level is 0.05. So again, we'll have 0.025 in each tail. Our n is 11, and so our degrees of freedom is 10. And so then we need to go get critical values. So let's get those. Okay, so we have a degrees of freedom of 10. So we'll be in the 10 row. And then our column, we have 0.05 for our alpha, and that's two tails, which would be 0.025 and one tail. So our critical values, 2.228, and its opposite, negative 2.228. Okay, and so then test statistic next. Okay, so our sample mean was 20.6 months, and the hypothesized was 18.7. The standard deviation was 7.8 months. And our sample size was 11. Okay, let's calculate. All right, so I'm getting 0.81. Okay, for our t statistic. And so then that's not in our rejection region. And so we'll fail to reject. Our H0. And so there's not enough evidence. Remember, we can't say that that supports the claim because we're already assuming the claim is true. We could say that there's not enough evidence to reject or refute the claim. There's not enough evidence to refute the claim. Okay, and then just for fun, the p-value method. The test statistic was 0.81, right? 0.81 would have been some kind of mythical last column over here to the right. And so our p-value would have to be bigger than 0.20, right, for that. All right, so then last example finally. So on this one, here it says a cereal company claims that the mean weight of the cereal in its packets is 14 ounces. The weights in ounces of the cereal in a random sample of 8 cereals is listed below, which tests the claim at the 0.01 significance level. We'll do both the p-value and critical value method just for fun. For this one, we were given the raw data. To save us a little time, I calculated some summary statistics in StatCrunch for us to use. So as before, we'll start with the hypotheses first. So null and alternative. So the claim is that the weight is 14 ounces. Okay, and so we've done a couple now that are two-tailed, so let me do one that is left-tailed actually, just so we'll have another example, just because it's more interesting. So let's say that the claim is, yeah, we'll make the null that it's equal to 14 ounces. And the alternative, the sample mean came out 14.05, so let's go ahead and make that bigger than 14 for the alternative. So it ends up one-sided. Okay, so then critical value. This will be right-tailed test. We don't have a population standard deviation, so we will be using t. Our degrees of freedom is going to be 7. So then let's go get our critical value for that. All right, so we have a degrees of freedom of 7. Our test is right-tailed, and we're using an alpha of 0.01. So one tail, 0.01, and the degrees of freedom of 7, that's 2.998. All right, test statistic next. So our t is x bar minus mu x bar. Are you getting sick of this yet? S over root n. X bar, the sample mean we'd found was 14.05. Hypothesized was 14. Sample standard deviation was 0.346 from StatCrunch, and our sample size was 8. Okay, so let's go ahead and calculate a test statistic from that. So 0.41. All right, so that's really not in the rejection region, right? So we're going to fail to reject our null hypothesis. All right, so then there's not enough evidence to refute the serial manufacturer's claim. As far as p-value method, taking a look in this row, there's definitely not a 0.41, which was our test statistic. If so, 0.41 would have been out here. We would have had a p that is bigger than that 0.10. Okay. All right, so what I want to do next is show you how you could use StatCrunch to do the whole hypothesis test. So let's see that now. All right, so I've started up StatCrunch here, and so let's start by putting in the data. I'm actually going to change the row or column label to be serial for this. And then let's go ahead and put in the data. So it was 14.6, 13.8, 14.1, 13.7, 14.0, 14.4, almost done, 13.6, and 14.2. All right, so we've got our 8 values in there. And so let's so we will put stat, and then what are we doing? We're doing t-statistics. We have one sample. This time, actually, we have the data. So we're going to do this. If we didn't, we would be using the summary information. But as it is, this time we have the data. So let's do that. We'll select the columns that we want. And we had used this to get us confidence intervals back in chapter 7. But now we're actually able to do the hypothesis test. For this one, our hypothesis was that the mean was equal to 14.0. And then our alternative was that it was greater, right? So we'll change our inequality sign to be a greater, and then we'll go ahead and hit compute. So we get a p-value of 0.3476, which is, like we said, pretty large. And so based on that, we're going to fail to reject our null hypothesis. All right, so that takes us to the end of our look at working on the mean. In the next video, we'll be working at doing basically the exact same stuff, but for the variance and standard deviation. So we'll look back at the chi-squared distribution, and but mechanically picking out hypotheses, drawing a little picture, looking up stuff in tables, a lot of that, and writing conclusions, a lot of that stuff is going to be the same. So let me know if you have any questions, and have a great day.